So there are various videos on YouTube of membrane separation for gate, but they are so much lengthy, so long that it it just feels like it is a short topic and we can quickly cover it. So this video we are going to quickly cover membrane separation, everything about it that is useful for gate, and in just a very short video that will help you to actually take out time for practice rather than just watching the long videos. So let's begin. What is membrane separation? Membrane separation is the separation of the components through a selective barrier. Okay, what do I mean by selective barrier? That means that only if this is a membrane, then only some part, that's mostly the solvent, would pass and the solute would be rejected back. This could be seen as like this, where this is a membrane and feed is coming up here, and what goes out is permeate. So this is permeate, this is feed, and what is rejected is retentate. So feed goes, R comes out as rejection or retentate, and permeate goes out. Now this membrane separation is a rate based process. So membrane separation is a rate based process, while processes like distillation, extraction, and absorption, they are equilibrium based process. Okay, now let's see what membrane separation has its driving force. So the driving force could be three. One is delta P, second is delta C, and last is delta V. So this is pressure, the pressure difference, this is the concentration difference, and the electric potential difference. Let's see the pressure difference first. So for delta P as a driving force, let's assume four we have four membranes with us. To understand the various four processes that we have, we can learn them by a very interesting thing, that is Munro. We can learn them by Munro. What is M? Microfiltration, U ultrafiltration, nanofiltration, and RO is reverse osmosis. Munro. We have suspended solids. What is coming through the first is suspended solids. So this, the pore size is the pore size is the most, and in RO the pore size is the least. So pore size decreases, pore size is decreases while we go till RO. That's why we have RO in our homes to purify water, because the pore size is the least. So we have suspended solids in the water. Okay, and we have macromolecules, then we have multivalent ions, and finally monovalent ions. Okay, from the microfiltration, suspended solids will be rejected while everything else will pass. Now for ultrafiltration, macromolecules will be rejected while monovalent and multivalent ions will pass. Then in the nanofiltration, multivalent ions will be reflected while monovalent ions will pass, but finally in the RO, even the monovalent ions will be reflected back or rejected, and water will pass through all the membranes. This is pressure difference, and now we can also see that this is the, in this way the size is actually decreasing. For delta C, that is concentration difference, we have processes like dialysis, then we have process like osmosis, and also pervaporation. Now we have in our syllabus delta P only, so let's focus on that only. And also the electric potential difference has elect electro electrofiltration and electrodialysis. Now let's see the key terms of membrane separation. First is flux, that is nothing but kilogram of solute divided by the area divided by the time. So this is represented by Na, the same as we represent in diffusion, and the unit would be kilogram per meter square second. Now let's see about the next term, which is permeability. Permeability corresponds to just like diffusivity, DAB. So DAB was flux upon so permeability is denoted by PM, and it is like diffusivity, so it is flux divided by the driving force gradient, which in this case would be delta P upon delta X, and the unit will be simple, it's kilogram per meter square second divided by ATM per meter, so it's kilogram per meter ATM second. Permeability is like DAB, while there is another quantity that is permeance. Permeance is PM bar, and this corresponds to mass transfer coefficient, and it is therefore flux divided by only the driving force, not the gradient, just like in the case of mass transfer coefficient. Then there is the transmembrane pressure, which is nothing but the dP by dx, the pressure gradient across the membrane, that is transmembrane pressure. Then we have three important terms which define the efficiency. So the efficiency of the membrane is defined by three terms. First is the R, or we can first say take a different thing, that is CR, that is conversion ratio or recovery ratio, convergence ratio or recovery ratio. Then we have the rejection, the solute rejection denoted by R, and finally what we have is selectivity denoted by alpha ij. I will tell you about these three. First, starting with CR. CR is conversion ratio. First let me show you the diagram again. Feed comes in, R goes out, and P goes here. Feed, permeate, retentate. This is R, so concentration, this concentration is Cp, this is Cf. So for the conversion ratio, the CR is nothing but how much Cp is there at the end. This is our main product, Cp, and upon Cf. This is the conversion ratio, or you can say recovery ratio. The next thing is, now one thing is that if a CR is more, that means Cp is more, which means that solute concentration is more, which means that our membrane separation is not much good. So it's always desired that our CR should be less so that it is a better process. Next is the rejection, or you can say the retentate, which is that rejected, so that R, but this is not the R, the flow rate. This I have denoted this solute rejection. So rejection is nothing but a kind of thing that you can think that it is CR upon CF, but it's not actually like this, but it's actually CF minus Cp upon Cf. Here in the diagram we can see F and CF, P, CP, R, but this we don't say CR, we actually take CF minus CP. This is the solute rejection. Now the solute rejection is like this. That means it is 1 minus Cp upon Cf, that is 1 minus Cr, conversion ratio. So this is the solute rejection, and now we have the selectivity. So selectivity denoted by alpha ij, kind of like relative volatility, or you can say the selectivity in the case of extraction, similar to this. What it is means that Cpi, because I is here first, so Cpi, let's say we have a membrane and I and J components are going, so I and J would be here also, and I and J would be here also. So how much? This is F R P. So how much in P compared to how much in F? So C Pi by C P C F I divided by C P J divided by C F J. Or you can say this is the CR of I and this is the CR of J. CR is conversion ratio. So this is selectivity. If alpha ij is 1, that means the amount of I in the feed is similar to the amount of I in the product compared to J, because both are in same quantity. That means no separation has occurred. If alpha ij is infinity, that means the denominator, that was Cpj upon Cfj, obviously Cfj won't be 0 but Cpj can be 0. This means that the J particle is not coming in the permeate, and this means that J is completely rejected, which indicates that we have perfectly semi-permeable membrane. Why perfectly? Because we don't have anything in J, and this was alpha ij means I above, J below, so we don't have anything in the J in the permeate, so perfectly it is rejected, so the membrane is perfectly semi-permeable. Next we have a molecular weight cutoff. Molecular weight cutoff, and what does it actually means? Molecular weight, this is our membrane. Let's say our feed is coming of, let's say, some molecular weight, let's take 100 for example, and this 100 is, let's say, our molecular weight cutoff, then at least 90%, at least 90% of this molecular weight solute would be rejected back. At least, it could be more, but at least 90% is rejected back. Then we can say this is our molecular weight cutoff, the molecular weight of the solute, that at least 90% is rejected. And this actually tells us about the membrane itself, that what is its rejection capability, till which molecular weight it can actually reject at least 90%. This is the molecular weight cutoff, and it also determines the pore size. Now let's talk about osmosis, because it is quite important. So osmosis, for this we take a very simple example. We have a membrane here, and in two beakers that are connected through this membrane channel, we have some solute here. There are 4 solute and rest water, while here we have only 1 solute. What will happen is that this one solute needs less water for to maintain some concentration, while this has 4 solute, so in that ratio it will need more water. So what happens is that this is a natural phenomena. Without any energy, the water here will like to move towards this way because this has more solute. So water from the low concentration, what I mean low concentration means only one solute is there, so that means less dense, less solute concentration. So water or the solvent from the low concentration will move towards the high concentration, and slowly this water level would decrease, this would increase. After at a time when both the concentrations would be equal, the activities would be equal, then there will be no transfer. Now this is osmosis. What if we want to reverse this process? Osmosis is a natural phenomena, and let's just see some equations that govern this. That is pi is equal to CRT. Pi is nothing but the osmotic pressure, OP. It's OP, osmotic pressure, and it depends upon the concentration. More the concentration, more the osmotic pressure. Now this is a natural phenomena, and let's just see what happens if we want the same thing to reverse out. We have a lot of water coming in our house. We put that water and the water has so much solute in it, but a lot of solute, but we want to just pass this water towards here. What is here? It has no solute at all. So typically what will happen, water here will actually move back because of osmosis, but we want to pass this water in the reverse way. This is RO, reverse osmosis. And what happens here is that we put some additional pressure. So we put some additional pressure to actually reverse the natural process. So let's take it in a way to understand like this. We have a membrane. In this we have concentration 1, there concentration 2, that would be 0. Feed is coming and the permeate is going, that is a pure water. There is P1, P2 pressure, while there is the osmotic pressure here due to concentration C1 and osmotic pressure here due to concentration C2. If we want to add some pressure to reverse the process, because we are going against the nature, what will happen is that our driving force will be actually the difference between these two minus these two. That means how much extra we need to put the pressure to actually go beyond the osmotic pressure difference. That is delta P minus delta pi. How much additional pressure we need than the osmotic pressure difference. Once this is clear that we have our driving force as minus delta P minus delta pi, we can find out the flux. Flux, we have two fluxes. One is for this water, or let's say the solvent, anything, let's say water. So flux for the water would be the permeance. Yes, we are not taking the gradient, but the permeance PMW, W here means water, into the driving force, that is delta P minus delta pi. Delta P is P1 minus P2 and delta pi is pi1 minus pi2, or you can say feed minus permeate, feed minus permeate. Next we have the next flux of solute. Solute flux is permeability. N's again, permeance of solute, and this time the pressure difference would be the concentration itself, because we know the concentration C1 and C2 here. So we have two fluxes here, and after rewriting the two fluxes, we know one more thing, that Ns, flux of solute by flux of the water or solvent, would be in the ratio of C2 by Cw2. But what is Cw2? Cw2 is the concentration of the water or the solute in the second part or the permeate. So permeate water concentration. This actually means that we're not talking about the C2, that is C2 is the solute, it corresponds to solute, but Cw2 is the equivalent concentration of the solvent in the permeate. If we say this is true, then in the same ratio, because of the fixed volume, this doesn't actually change anything, and this will be in the same ratio. Now we will put the equations of Ns and Nw from what we derived, what we found out earlier. In that case, this would be Ps upon Ps bar upon into C1 minus C2 upon Pm of P, this is Pm Pw Pmw bar into delta P minus delta pi. This would be in the ratio of C2 by Cw2. Next we can put this over here, and C2 and Cis over here. If we put this like that, what we found out is C1 minus C2 upon C2 is equal to Pw bar and Ps bar into 1 upon the Cw2, this thing, into delta P minus delta pi. Now this thing we can write as 1 minus, we can write C1 by C2 minus 1 and going 1 over there, but let's just take this term as B. Okay, and this term, now if we see Cw2 is here and this is there, this term has a unit of atm, while this is a unitless term. So the B, this is our B overall quantity, so this B will be atm inverse. Let's change the things now over here. This is our B into delta P minus delta pi, and this is equal to C1 minus C1 by 2 minus 1. Now let's rearrange this, put 1 over there, and if we see C1 by C2, then this would be 1 plus B delta P minus delta pi. Now let's take the reciprocal, that is C2 by C1, that is actually Cp upon Cf. This is nothing but 1 plus B delta P minus delta pi. And if we want to find out the R means rejection, the solute rejection, that is actually Cf minus Cp upon Cf, we can find it out by C1 minus C2 upon C1, or we can say 1 minus C2 by C1. So let's take that. So we have C2 by C1, C1 by C2 was this 1 plus, and now we have, if we take the reciprocal, that means whole to the power minus 1, then this is this. If now we need to take 1 minus C2 by C1. This is our CR, which is nothing by 1 minus 1 upon 1 plus B delta P minus delta pi. And finally, if we rearrange all of this, we will get that 1 minus C2 by C1 is 1 up minus Cp upon Cf. This is our CR. CR is Cf minus Cp by Cf, or we can say C1 minus C2 upon C1. This is nothing but 1 plus B, this minus 1. So this is B into delta P minus delta pi upon 1 plus B delta P minus delta pi. Let me write it clearly again. This is B delta P minus delta pi upon 1 plus B delta P minus delta pi. This is a final equation, and we know that what is B here? B is nothing but Pw bar by Ps bar into 1 upon Cw2. One way to remember is that is BWS, and W will cancel. In that way it will not cancel, but this is a way to remember. So BWS. So these are the whole equations, and one thing to remember is that at equilibrium what will happen is that the flux would be 0. That means delta P minus delta pi would be 0. That means delta P is equal to